Hey, P-Psych. Happy Tuesday. Let's do some image review. This should be, I believe, the sixth go of it. Share screen, do desktop, minimize that, and here's an image. Okay, so we got a couple of different things going on here. The prompt from at least our textbook for this one would be, what is color constancy? Should be under the box. Yes, there we go. Color constancy. So I'm going to do countdown. Okay, if we're talking about sensation and perception, color constancy, you should have something or think of something to the effect of what we expect to see here on this image is you don't see these blue boxes in the middle of all of these yellow ones as being much of a different color. It should be constant or consistent, even though you're not actually getting that same light or the same wavelengths from all of those different things. You are literally sensing a slightly different hue or wavelength of the blue. So this blue, that one that would be down here, is going to be different from that one, is going to be different from that one. Although your brain will almost certainly tag it as being the same thing, or the yellows should hold true. These are going to be nearly black colored boxes, but your brain's going to see that as being over down to the side. It's going to be a shadow version of it, or a more shaded version. So we have a light, and then a medium value, and then a really dark. You see it as being yellow, even though it's not actually going to be that same yellow. They're completely different colors. And you view the blues as being probably, you should, the same sort of a thing. We get a similar sort of with the background, that checkerboard kind of a thing going on. That same effect takes place, and we can see it on the next thing here. So if we're looking at, in this case, what looks like a checkerboard or a chessboard, you get that pattern. You have whites and black, or white and gray, however you want to think of it. And then if you've got a sphere here, which again is going to have a couple of different effects to it. You've got shadow and highlight. The shadow of that A right there, if we move over and down, in this case of like how a knight's going to move, you get the B here, and you see them as that's a white, that's a gray, but in effect, because of brightness constancy, you assume that there's going to be a difference in that. That's not the case. The A and the B are going to be the exact same thing. For an explanation on here, we perceive, if we're talking about like the actual, the textbook definition for brightness constancy, we perceive an object as having the constant brightness, even if the illumination or the amount of light is going to change or be different. That relative luminance, that difference in the amount of light that you get, is going to reflect and change what either the object is and the surroundings. It's going to affect or impact your perception, your top-down processing, what your central nervous system thinks is going on for all of these different things. So it becomes slightly different, even though A and B should be the same. You sense the same thing. You perceive them as differently. That constancy, or keeping it straight in your head, is the effect, is that brightness constancy. Another effect for constancy, in this case, it's not going to be for the color or for the illumination, for the brightness of it. Now we're going to talk about shape constancy. That effect is going to be illustrated here in this door. You see a rectangle, you get that sensation, the sense of, in this case, it's going to be the lines, and you perceive it as a door, but as it starts to move, it turns into a trapezoid, and it's a different shape that hits your eye, hits your retina. You don't perceive it as being a different thing. You don't get confused at every degree change of whatever the object is. It doesn't become something different, at least not in your mind. You tag it as the same thing, and you're not confused, and you're not seeing it as a change. Otherwise, every single time you moved your head, something different would have to take place in the world, and you'd have to reevaluate what every object is, what every color is. Is it appropriate? Did it change? Does it move? Does it have some sort of a need for immediate attention and stuff like that? The strange thing, and this would be a really difficult question on an AP exam, but if you got something about our ability to see, our eyes actually always need to get a little bit of a change in wavelengths or in movement of stuff. So to try and take care of that, our eyes actually are constantly twitching just a little bit, almost imperceivably, so that we can get a change in the image that's coming in. So if you've seen, for example, like Jurassic Park, the original one, they say stand still, and the dinosaur, the Tyrannosaurus, won't be able to see you. It's kind of would be true even for us. If you could stand still and stop someone's eye from twitching, that little amount of muscle movement in the eye, so it wasn't picking up on the different stimulation as light comes in. we do see that almost like habituation. Your eye becomes habituated or bored with whatever it is that's going to be sending the signal, and you don't need to pay attention anymore. So if you were able to account for that, you could kind of make yourself invisible to someone if their eye wasn't twitching, or if you could like move at the exact same rate that they were twitching, would, I assume, would be impossible to actually calculate and come up with, but it'd be a bizarre and sort of dumb superpower. All right, there's shape constancy. Let's do a different one. Now we're putting together a whole bunch of different things in order to get this effect. If you remember from forever ago, this would be a thing that we had looked at, and these people are going to be basically the same size, but how is it that we can look and see the drastic difference that you've got someone that's going to be super large over here and then super tiny over there, kind of a Willy Wonka thing that took place. All right, what is it? How does it work? Okay, this was the Ames room, A-M-E-S. And in this case, it's going to be an illusion or a perceptive thing that we can mess with. A bunch of different effects are taking place here to cause us to perceive as if there's a difference. So it's going to be dependent that you've got someone who's sitting at an appropriate focal point. So you need to be centered as you're viewing it at the end of, like the opposite end of a room. And then we're going to have things take place. So if you look, the person on the left is going to be way back in the actual corner of the room, as opposed to the person on the right, the one that's going to look large. They will be physically closer to you. And your brain perceives sizes differently. If the thing's going to be big, it's probably going to be near you. If thing's going to be away, it's going to be smaller. Sort of like if you have someone in the room with you, or you look across the room, even like a door frame from only like 15, 20 feet away from me, I can do like the, you know, squish their head like a grape, or squish the door frame. But if I was standing truly close to it, it would appear as its actual size. And most doors are what, 6 feet, 6.5 feet? I don't know. We also get that the room will be shrunk down. So if we look at the girl on the right, the ceiling is downward and the floor is elevated. So it looks like she's taking up more of that space in the frame or in the room. And she is taking up more of the space, but it's an illusion that it's actually the same space. It's not, because the room is going to be closer and the room's going to be shrunk down. And then all of the different things here will be correspondingly smaller. And we're using that linear perspective off into the side so that it looks like the picture frames will be different. She takes up only a small space of it. She takes up a huge amount of it. We put all of these different things together closer, and we shrink the proportions, and we've got that. Oh, and it looks like you've got some sort of a giant and a teeny tiny. And if they were to cross over somewhere in the middle, as this one goes down and the other one comes up, then we would see that they are about the same. And then it's going to switch as they go over, larger and then smaller. And after a moment, it probably looks fairly legit if you constructed a good version of this, of the Ames room. All right. Hey, a sensory organ. This should be a good one. So we've got parts of the ear. 10-ish is what we got. I would assume you can easily draw and label. Here we go. Let's do some parts. Ear parts, ear parts. So the thing that we're actually going to sense would be sound waves or pressure. You could do vibrations if they ask you to do something on what it is that you're actually going to be stimulated with for audition or for hearing. Same thing, audition is hearing. Sound waves are going to have to, I don't think this illustration is going to do the, this portion of the outer ear is going to be the P-I-N-N-A, pinna, that helps to focus it. It does help. All right, you want that little bit of a flap to pick up more of those sound waves and help funnel them in. Of course, you can hear without it, but it's going to be something that will be of benefit to you. And then once it gets funneled in, it's going to go down and through, and to some extent here, you can see the waves kind of get a little bit, I think compressed would be an appropriate word as it moves in here. We're going down the auditory canal or ear canal. Again, everything's going to be ear, ear, ear. It's a little bit redundant. They'd never take points off on the AP exam if you said ear, 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 ear canal, outer ear, inner ear. So you don't have to just say canal. Same thing, doesn't really matter. Okay. So we get focused down, we go through the canal. We're going to hit the very first part here. Boop, would have been the noise we made when we drew and labeled it. Seems like forever ago. This is going to be the drum, eardrum, or tympanic membrane. Same exact thing. Outer ear, all the stuff in theory you would be able to touch. Then we go from the outer to the middle ear, and the middle ear is going to be just, and we don't have it on here, just the three little bones: hammer, anvil, stirrup. Hammer, anvil, stirrup. Hammer hits the anvil, shakes the stirrup, would be the three little bones here inside of the middle ear. Ossicles, Ossicles, Ossici. I don't think they would ask you that, but either way, the bones of the middle ear. And then these are going to hook up with what we'll now move on to as inner ear parts. Inner ear parts that we're going to be looking at. I don't want to go that far back. I don't want to go. Yep, there we go. Hammer, anvil, stirrup. The stirrup connects to the oval window where the stirrup attaches to the next part. Here is going to be the cochlea. And the cochlea is the thing. The cochlea is the spot or the part in which we're going to take and change whatever the stimulus is for any sense. So the stimulus for hearing sound will be turned into an action potential at the cochlea. The super fancy ass term that I want you to know for that will be transduce. To take and turn in that stimuli into an action potential is called transduce, transduction. So the retina, in particular the rods and cones, are the part that transduce light wave into action potential, so it can go on to your thalamus and then your occipital lobe so you can see. And when we're talking here with the ear, with audition, it's going to be the cochlea, or those little teeny tiny hairs that will be on the membrane or the basilar membrane, those little hairs that will vibrate when fluid moves over them because of the shaking of the hammer to the anvil to the stirrup and then over through the cochlea. As that fluid's going to be washed over, the little hairs vibrate. If you were to unroll it, it looks like, you know, just a little, starts as a snail. You unroll it and it would look like your arm, is what we did in class. And as the hairs are moved, they're going to hear various tones, or with the frequency with which they get vibrated, you can hear different pitches. Then that signal is going to be taken on to and through via your auditory nerve. And then up top, we've got the semicircular canals up top there, and that's not going to be for hearing per se, but that's going to be that sense of balance. So you've got the hand turkey that we drew on top, and you've got liquid just like in the cochlea. The liquid that's going to be on those semicircular canals, in this case, pushes down, so you know that up would be the opposite direction. So if I put my head to the side, suddenly that fluid tips and there's empty space where the up is. So you always know which way is up and you don't get confused, unless you were moving around with some sort of rapidity. If you spin around in circles and then you get confused because that liquid keeps moving for just a brief moment until it settles down. Or if you lose, you can have other senses to some extent intermingle and kind of confuse that. Yay, ear. Hey, this is a good one. So we've got the best term for this is going to be called a reflex arc. Take a look at it, talk through it, and then I will join you in just a moment. Okay, so if we're talking sense, in this case of pain, nociception is what we would actually call that. You feel that in skin, you feel that in other tissue as well. That sense has to go from your sensory neurons, from whatever organ we're talking about, up to and through thinking parts. So you've got tissue that would be injured. If you step on a tack, or if you step on a little thumbtack like that, or in my case, it would be like Legos, which surprisingly aren't around, or little like micro machine cars. I step on it and the signal's going to go up through afferent neurons or sensory neurons until it gets to, this is a weird place for it to go out on the bottom of the calf there. It would go up to your first thinking part it's going to encounter, which is going to be your spinal cord. Yeah, great. Not a bad cross section of the spinal cord here. And the signal's simultaneously going to have a break, and two things are going to happen. One portion of that signal is going to go up to your head so you can think about or recognize you've stepped on something, and you're going to yell at your kid. You're going to yell at your whoever left something on the ground, and I don't know why you're walking around in a place that's going to have injurious things like that. And you're also going to get the signal that gets sent back through motor neurons, because you have interneurons, thinking neurons here in the spinal cord. So one signal goes up and eventually you'll say, ow, and the other one's going to go down and move your foot emergently quickly. You're going to need to move that foot so you don't harm more tissue, and your foot's going to come up in a reflex before you even recognize or label cognitively what's happened. So your foot starts to move off of it super fast, and then probably you would scream or think about it or notice whatever is going to be going on. That you have, you know, a foot with some sort of a gash in it, or there's blood somewhere, or whatever's going to be going on. So a couple of different things. One more time. This is called a reflex arc as this happens. If you go and they hit you with a reflex hammer in the patella or just below it in that little tendon there, you're going to kick. You don't think about it. It just happens automatically. It's an autonomic function of the nervous system. So those things just take place. And we've got all three sets of neurons or types of neurons you would need to know for the AP test working here. Sensory to feel it. Interneurons, the thinking ones that would label and recognize, oh, something happened. And then the motor neurons telling the muscles to move so that your foot would actually come up and execute whatever the decision making that had happened or taken place was. Sensory, interneurons, motor neurons to move. All of this in a reflex arc. Different sense stuff we've got for what things are you capable of tasting? And you should know at least 5 of them. Okay, and then a description for them. I don't know, it's a good description for them, but what's the indication we think? So a good source of energy would likely come from sweet things. It is a quick and easy way for your body to get a source of energy in something that would be super sweet. Fruit, or clearly something that would be super sugary, immediately can be used as an energy source. So we think that's also, since it's going to be so quick and easy to get, why like infants, for example, enjoy sweet stuff. All right, if we're talking about sodium, and this would be definitely an essential physiological process thing, you need sodium so neurons can even fire. And this is why we take or intake salt. Salty stuff is something that we would want or need. Okay, if we're talking about acidic tastes, generally that would be a description for something that would be sour. Adaptively, that might be why kids, for example, don't really tend to prefer those, or at least not a whole lot. And if we're talking about that same idea, like tastes that kids definitely, we're talking little kids, do not like, this would be one example, though the best example probably would be bitter. We're talking about vegetables or plant-like tissue that's going to be potentially poisonous. So they would want to stay away. We think that would be an adaptive function for it. Why was it good? Kids don't like bitter? Because it could be poisonous. Plants could be poisonous. You don't want them just eating everything. Although they do. They put everything in their mouth. Okay. And then if we're talking about protein repair for tissue, stuff like that, we would also include umami as the one taste likely that people end up having a hard time coming up with on their own if they've never actually studied in any academic setting what things officially we have. In this case, these all appear or take place on taste buds. Mostly, yes, they're on your tongue, but not entirely on your tongue. They're throughout your palate. So you should be able to taste these things anywhere in, you can do tongue, you can do a little bit of roof of your mouth, kind of sort of on your cheeks and stuff like that. Teeth don't taste anything, but they do have an ability to pick up on some temperature differences. So if something's going to be really hot or if it's going to be really cold, that can be part of the process there. Okay, so all 5 of those things. And the one thing sometimes that people will include erroneously in what it is that you can taste would be like spicy. In that case, spice is just an indicator of pain. It's a nociceptive sense that happens also in your mouth. And a little bit of that can add to the overall feeling of enjoying a meal. If you get a little bit of crunch to it, you have that textural change, you get changes in temperature. Also, because your senses intermingle strongly, things that look appealing, right? It looks good, and then you get a smell to it. Most of your sense of smell actually accounts for what it is that you're tasting. Your taste is diminished greatly, and the estimates sometimes are even up to like 80% of what you're tasting is actually smell. Plug your nose when you're eating the next thing, and it dulls your flavors drastically. All right, so I'm looking at just over 20 minutes now. I assume I should give it a quit, call it a day here. I hope everything's great. If I put some things on Gradebook, for the first, I don't know, weekish stuff of a slew of participation thing. If you're missing some stuff, please email me, send it to me, and I will get it updated and get grades updated as well on Infinite Campus. It's largely just participation stuff. Let me know if you need something or have questions. All right. Have a good one, guys. We'll talk to you soon.